Let me recall to you the proper mathematical definition of a Markov chain, because it is more subtle than it appears at the first sight. So a stochastic process, which is indexed by the integers as time parameter space, and which assumes values in a countable state space S, is called a Markov chain if the following holds true. If we give ourselves a sequence of time points of observations, where the latest time point is interpreted as the only future time point. So we assume we had made a couple of observations at time points k1 to kn. And if we want to make a computation about the probability that the process behaves in a certain fashion at time point L, providing that we have certain amounts of information which we obtain through observation of the process in these time points. So if we have these chosen time points and we have certain test sets for these observation time points, let us call them like that, E1, E2, and so forth, En, which are all subsets of the state space. And if at the latest of all these observation time points, Km, we have a single element observation set of states, which then is just one state, S and S, and if we fix an arbitrary future collection of states, so states which are supposed to be attained in the future, and if we then ask ourselves, what's the probability that at the future time point XL, at the future time point L, the process XL assumes states in this test collection of future points, conditional on the observation that we made. Namely, we observed that at moment K1, the process assumed values in the test set E1. At moment K2, the process assumed values in the set of states E2, and so forth. And finally, at the latest of the observation time points, we had observed a precise location of the process, namely that it has attained the state S. So we ask again, let us say what we are computing at this point on the left-hand side is we are asking for the conditional probability that at future time point L, the process assumes values in a fixed but arbitrary test set F of states, conditional on a whole array of observations that we made at a certain sequence or collection of finite time points in the past, and where among all these observations we made, the latest one, which is to be interpreted as the current observation point, we have precise information on where the process is located. So if this conditional probability, that's now the requirement, if this conditional probability is just the same as if we had asked for the analogous future behavior of the process, but just providing the information, the precise information on the latest of these observations, namely if we know where the process has been exactly at this latest position, at this latest time point Km. So if these two conditional probabilities are the same, then we call the process a Markov chain. This definition says that for the computation of probabilities for future behavior, given a whole sequence of observations on the process, the only thing that really matters is the very latest of all this information. In addition, we call this Markov chain time homogeneous if the latter probability, the latter condition probability, depends, of course, on the test set F and the state S, but in terms of the time variables, it depends only on the difference of the time variables. In this case, this Markov chain is additionally called time homogeneous. If we have a time homogeneous Markov chain, then we introduce two types of data which are associated to this Markov chain. One is the so-called transition matrix, or transition probability, or transition kernel, also sometimes it is called. It's the collection of one-step transitions for all pairs of states I and j from the state space. We can talk about the conditional probability that the process makes a step from state I to j in a single time step. This collection of probabilities Pij constitutes a matrix which is indexed by the collection of states in the state space, and we call this matrix the transition matrix. It is a stochastic matrix in the sense that all entries of this matrix are non-negative, and the rows in the matrix, the sum of the entries in each row is 1. And the second datum which we associate to a Markov process, or the Markov chain, is its starting distribution or initial law, which is just the probability to find the process at starting time in a certain state, because we can think of stochastic processes or Markov chains which do not start in a given fixed position, but which may start in a randomly chosen position, and then there must be some law, some probability distribution for this initial choice, and this probability distribution is lambda. It's called the starting distribution. The following simple finite Markov chain is meant to be an example that it is really necessary in the definition that we just gave that the latest observation that appears in this conditional probability equality, that the latest of this condition, the latest of these conditions is really a condition which observes a precise observation at a single state for the process. To illustrate this, we consider the following example. Then we have a Markov chain which can assume only 6 different states. So it's a finite state space, therefore we call it the finite Markov chain. And the transition probabilities are specified. It is probably a kind of artificial example, but I tried to cook up one which is as small as possible in order to show why the definition here is a little subtle. Then we have state 1, which we shall use further on as a starting state. We could choose other states, but at the moment we want to choose state number 1 as starting state. So the initial distribution will be just a Dirac delta function, which is concentrated on this state number 1. And then from there we can make choices with equal probability to jump to state 2 or 3. And then there is no randomness involved, because then the chain will, in each of those 2 respective states, will continue to jump to states 4 and 5 respectively. And then from 4 or 5 there is a possible transition to 6 with probability 1/3 from 4 and 2/3 from 5, and with the remaining probability from 4 or 5 the system goes back to the initial state. So that's the Markov chain. That's the specification here of this kernel. I should also probably say that the state 6 is absorbing, as we shall say, because when we are sitting in 6, we will return to 6 each time. So once we are at 6, we will be trapped there forever. Okay, so the corresponding transition matrix here is a 6x6 matrix, and I wrote it here. You can see that the sum along the rows is 1, if I didn't make any mistake, but it appears okay. So, and now I want to show that we have to pay attention that regarding this latest of the conditions in the sequence observations, namely that things become a little inconsistent, it appears, but they actually do not, if we have more than just a single state observation in these conditions. Okay, so in order to do this, I give a model for a proper mathematical model for this Markov chain, and I want to consider this Markov chain only up to a finite number of time points. Namely, I want to consider it in 4 different time points, time point 0 up to time point 3, which makes 4 different states in which the process can be. At time 0, it makes an initial choice, and then it evolves over time. So it eventually makes 1, 2, 3 transitions at most. At least that's the time axis on which, or the time horizon on which I want to observe the Markov chain. So therefore there's a very finite and very simple probability space which I can use in order to describe this. Namely, I choose here as path space the space of all sequences of length 4 where in each coordinate of a sequence I have a state indicator, which is a number between 1 to 6. So that's my state space, that's my path space. So each element from this omega space is a sequence of 4 different states, which represents one trajectory through the state space that a possible Markov chain could take. As I said before, I want to start the whole process in my particular example from the deterministic initial position 1, which therefore says that my initial distribution lambda is a Dirac delta function at this one position, or written as a vector, it just says it's a vector which has everywhere 0 except at position 1, where it is 1 for this probability of 1 to start there. As usual, we shall identify here a function on a discrete space, on a countable space, with a corresponding vector, which might be infinite. Then, as in the previous lecture, to each such a possible sequence of states, from S0 to S4, from S0 to S3, we associate a path probability for this path. So this sequence, whether it's finite or non-finite in length, we shall in the future denote as a path. And to such a finite length path, we can associate a probability value, a value between 0 and 1, which is the product of the transition matrix entries for the corresponding transitions which we have between those different states, multiplied with the probability which is read off from the initial vector for the initial state. So this path here would be associated with the path probability, which is just the product of these transitions. So we have a lambda S0 for the initial position, that's the probability to choose S0 as the initial position, and then we have these transitions which are chosen in an independent fashion, but in such a fashion that they match to the sequences, to the sequence of states given. And for a whole collection of states, of a whole collection for a correction of possible sequences of states, so for a whole subset E of this path space, I define the probability just to be the sum of all these individual probabilities of the paths which fit into this collection of paths E. So every set E here of this path space is a collection of paths, and therefore the probability for this collection of paths is just the sum of the individual probability for those paths which appear in the sum in this set E. So in total we have set up a finite probability space, namely the probability space for finite length paths, where here the length of the path is 3 or 4, depending on how you count the initial state. And then I can define a sequence of random variables on this probability space, which basically is just the evaluation of the corresponding coordinates. So xi for I from 0 to 3 is now a collection of random variables, namely the ith random variable I want to observe maps such a path just to its ith component or its ith entry. So this is the sequence of evaluation maps. And then it's a little exercise, but not too complicated, to show that this sequence of random variables on this very explicit probability space realizes, in fact, a lambda p Markov chain when I observe only the first 3 or 4 steps. Now we want to show that it really matters for the verification of the Markov property whether the latest observation, which you include in your set of observations for the computation of the conditional probabilities, whether this latest information is a precise information or whether it involves a collection of states. To see this, let us assume we want to compute the following conditional probability, namely that the probability for the process to be at position 6 at time 3, conditioned on the event that the process at time t was in one of the two states 4 and 5, and that in the moment even before that it was at position 2. Now, if we look at the graph which is associated to this Markov chain, we see that the joint condition of the process being in one of the states 4 or 5 at a certain time and being at position 2 at the time before that is just the same as saying that the process at the previous time was in position 2, or which is just the same as saying that the process was at the time after at position 4. So effectively, the additional information on the pre-latest time point will select, in this particular example, will select among the two options we have specified in the condition that corresponds to the latest time point. So what I wanted to say is that this condition here differs with probability 0 from the condition here, which is just said, okay, obviously at time point x, at time point 2, the process must have been at position 4, and by omitting this condition x1, I have made no mistake, because that's the only possibility that remains by specifying this sequence of 2 positions. And then I am back at the condition, at the usual condition probability that we have to evaluate for the computation of the transition probability. Namely, this is the matrix entry P46 of our transition matrix, which is 1/3. So it's the condition probability, or the one-step probability from room 4 to room number 6. And if you look back at the graph, how we specified the whole thing, it's 1/3. Okay. Now, if I take another condition in the pre-latest observation time point, namely I compute the same probability for being in 6 at time 3, given the same latest condition regarding the time point which is before that, namely at time point 2, I want to see that it was in one of the states 4 and 5. And I now want to furthermore condition on the event that at the time point before that, the process was in position number 3. Then by the same consideration, this is just the same as saying that at time point 2, so at the latest observation, it must have been in position number 5. So this is just, if you like, the lower leg of this graph, saying it, the process before being in 6, it was in one of the 2, 4 or 5, and even before that, it was in 3, just means nothing but that the process before being in 6 was in 5. So therefore, this condition probability is just the same as asking what's the condition probability to be in 6 when you are in position 5 before, and we read off from the graph that this is 2/3, just by the way that we designed this example. This is the lower leg here, so this probability here is a 2/3 by definition of all these quantities. And we see that this is not the same as 1/3. So what we see here is that in this example, the additional information that here was specified, which predates the latest information, has a profound impact on the value of the resulting conditional probability, because in the latest information we still have some ambiguity left, and the predating information will make a selection which of the possible choices for the very latest observation, before we actually do the prediction for the future, which of the possible choices will have been observed in the end. And this ambiguity can only appear if the latest observation, which is specified in these conditional probabilities, is not single valued. then there is an additional choice or an additional mixture of different possibilities, and to what extent one of those possibilities is actually attained will then be influenced by the additional information which can be provided by observations which predate the latest observation. Okay, so this example shows that when you have more than when you have not a precise information on the latest state of the system before you want to make a prediction, then the Markov property cannot hold in its naive form. The Markov property can correctly be formulated only when the latest observation from which you want to make an interpolation towards the future, when the latest observation is precise. But if you do have a precise latest information, a precise information on the state of the system at a given moment of time, all other information that comes from the past is no longer